Welcome to a deep dive into the fascinating world of physics. And today's journey is especially exciting because we're taking a cue from your own research stack on the history and pedagogy of physics. We're about to uncover how some historical breakthroughs connect with how we understand physics today.
It's amazing how those connections often emerge. When we dig deeper into the historical context of scientific discoveries, it enriches our understanding in ways a textbook simply can't.
Absolutely. Now, you might be thinking, a pendulum? Seriously. But trust me, this deep dive is going to reveal how this seemingly simple device played a pivotal role in shaping scientific thought. In fact, Michael R. Matthews, whose work you've included, makes a compelling case for why the pendulum deserves way more credit than it typically gets.
Mm.
What's fascinating about the pendulum is that it appears so simple, almost mundane, yet it became this incredible tool for scientific inquiry, revealing profound truths about the universe.
It's a perfect example of how looks can be deceiving in the world of science.
So let's rewind the clock back to the scientific revolution and peek into Galileo's workshop. He was meticulously studying the pendulum, even using flowing water to precisely track time. Talk about dedication.
Oh, absolutely. Galileo's experiments with the pendulum were groundbreaking, and his meticulous approach laid the groundwork for a deeper understanding of motion. For instance, he accurately observed the difference in swing time for large and small amplitudes.
Okay.
However, and this is where it gets really interesting, he attributed these discrepancies to external factors like friction.
Wait, so he nailed the experiments but missed a crucial aspect of the interpretation. What happened?
It was Christian Huygens who later realized that Galileo's misinterpretation stemmed from the pendulum's movement along a circular arc.
Okay.
Huygens discovered that a perfect pendulum wouldn't swing in a circular arc, but in a cycloid, a curve traced by a point on a circle rolling along a straight line.
That's a pretty significant aha moment in the history of physics. It makes you realize that scientific progress isn't always linear.
Right.
Even geniuses like Galileo can overlook key details, paving the way for future discoveries.
Precisely. And Huygens' insight about the cycloid wasn't just a geometrical curiosity. It had profound implications.
Okay.
It allowed him to derive the formula for the period of a simple pendulum, T, 2LG. This elegant equation beautifully links the period of a pendulum swing to its length and the acceleration due to gravity.
And this brings us to another titan of science, Isaac Newton. I understand the pendulum was instrumental in his work as well.
Absolutely. Newton's work was deeply intertwined with the pendulum. He used it to calculate the gravitational constant g, refine the accuracy of timekeeping, and even, fascinatingly enough, to debunk the then popular concept of a mechanical ether filling space.
Hold on, the pendulum helped disprove the ether. How so?
Well, back then, many believed that light, like sound, needed a medium to travel through.
Okay.
This proposed medium was called the ether. The pendulum was a key player in experiments designed to detect this elusive ether, ultimately demonstrating that it didn't exist.
Wow.
This paved the way for a new understanding of light and its propagation.
The pendulum's role in debunking the ether is a great example of how even seemingly simple tools can challenge deeply held beliefs. And speaking of challenging beliefs, you've also included some fascinating research on the history of mechanics.
Yeah.
It's amazing how our understanding of something as fundamental as motion has evolved over time.
It's a testament to the power of scientific inquiry to overturn long-held assumptions. For centuries, the prevailing view of motion was rooted in Aristotle's ideas.
Right.
He believed in two distinct types of motion, natural and violent.
So natural motion would be like an apple falling from a tree drawn towards the earth,
Right.
while violent motion would be like pushing a boulder uphill, requiring a continuous force.
Precisely. Aristotle believed that objects had an inherent tendency to move towards their natural place, with heavier objects driving downwards and lighter objects upwards. Any motion deviating from this natural tendency was deemed violent and required a continuous external force. However, this Aristotelian view, while intuitive, couldn't account for things like projectile motion, setting the stage for a radical shift in thinking. And that's where figures like Galileo and Newton come into the picture, completely revolutionizing our understanding of motion.
Newton's laws of motion truly changed the game.
Right.
Inertia, forces, action-reaction pairs, these concepts formed the bedrock of quantum mechanics.
Yeah.
His work provided a mathematical framework to describe motion with a level of accuracy and comprehensiveness that was unprecedented.
And yet, even with these fundamental principles established, teaching some core physics concepts can still be surprisingly challenging. Take optics, for example.
Okay.
The research you provided on teaching the speed of light reveals that even this seemingly straightforward concept has a rich and complex history.
Light speed, it's physics 101, right? What makes it so tricky to teach effectively?
Well, you'd be surprised. Back in the early 19th century, there was a significant debate about whether light traveled faster or slower in denser mediums, like water or glass, compared to air.
Hmm.
Two prominent theories attempted to explain the behavior of light, each with its own set of underlying assumptions and mathematical models. This debate wasn't just an academic exercise. It had profound implications for our understanding of the nature of light itself.
So it's a real scientific showdown. Which theory ultimately prevailed?
Well, that's the beauty of science. It's ultimately decided by experimental evidence.
Right.
In this case, around 1816, Augustin Fresnel and François Arago conducted a series of ingenious experiments that definitively showed light travels slower in denser mediums like glass compared to air.
Wow.
Their findings settled the debate and underscored the crucial role of experimentation in validating or refuting scientific theories.
It's fascinating how these historical controversies and the experiments that resolve them can make physics so much more engaging for students.
Right.
It shows them that science is a dynamic process, a journey of discovery, not just a static collection of facts in a textbook.
Absolutely. And it's not just optics where teaching challenges arise.
Yeah.
You've also shared some interesting research on the difficulties students face when learning about electricity,
Oh, okay.
particularly the concept of electrical potential.
I can see that.
Voltage, potential difference, these concepts can seem pretty abstract at first.
Yeah.
What are some of the common misconceptions that your research highlights?
Well,
One common stumbling block is that students often mix up potential difference with charge.
okay.
They might incorrectly assume that a higher potential difference automatically means more charge, which isn't necessarily true.
Right. It's not about the total amount of charge, but rather the potential energy per unit of charge.
Precisely. And another frequent point of confusion is the role of batteries in a circuit.
Okay.
Some students tend to think of batteries as supplying a constant current, almost like a pump, pushing charges around the circuit.
Okay.
However, batteries actually maintain a constant potential difference, which then drives the flow of charge.
It's like the battery sets the stage, creating this electrical landscape, and the charges then flow according to the potential difference in that landscape. And this is where those teaching challenges come in, helping students develop that accurate mental model of how electrical potential works.
Exactly. Your research highlights some intriguing approaches to tackling these challenges, such as using analogies to familiar systems or incorporating interactive simulations to help students visualize these abstract concepts. But perhaps we can delve deeper into those pedagogical approaches a bit later. For now, let's transition to a realm of physics that takes abstract to a whole new level. The world of quantum mechanics.
From the elegant mechanics of pendulums to the complexities of electrical circuits, our exploration of physics has taken us through some truly fascinating territory. But now, let's prepare to enter a realm where intuition often fails, and the very nature of reality seems to shift beneath our feet. The enigmatic world of quantum mechanics.
Ah, yes, quantum mechanics, where particles can be in multiple states at once, where observing something can actually influence its outcome, and where even seasoned physicists find themselves questioning the very fabric of reality. It's a testament to the boundless capacity of the human mind to probe the deepest mysteries of the universe.
And teaching this mind-bending subject is no small feat. You've included some insightful research on the challenges of teaching quantum mechanics, and I'm curious to delve into those a bit deeper. What makes this area of physics so difficult for students and even seasoned scientists to wrap their heads around?
Well, one of the primary hurdles is that many core quantum concepts seem to directly contradict our everyday experiences. Take, for instance, wave-particle duality, the idea that light and matter can behave as both waves and particles. This concept is fundamentally counterintuitive. In our macroscopic world, waves and particles seem like distinct entities, yet in the quantum realm, this distinction blurs.
It's like trying to imagine an object being both a rippling wave in a pond and a solid pebble at the same time.
Right.
And it's not just wave-particle duality. We've got superposition, the possibility of a quantum system existing in multiple states simultaneously, and entanglement, where two entangled particles can influence each other instantaneously across vast distances, seemingly defying the limits of space and time.
Precisely. These concepts can feel incredibly abstract, and finding relatable analogies or visualizations to make them more accessible is a significant challenge in teaching quantum mechanics. For example, the classic thought experiment of Schrödinger's cat, where a cat in a box is in a superposition of being both alive and dead until observed, often leaves students more bewildered than enlightened.
Schrodinger's cat always seems to spark more questions than answers, but that's part of what makes quantum mechanics so captivating, right? These seemingly paradoxical ideas push us to expand our thinking about the nature of reality. And speaking of paradoxical, how can we forget the measurement problem? It's a concept that has plagued physicists and philosophers for decades.
Indeed, the measurement problem cuts to the heart of quantum mechanics, questioning how a quantum system, which can exist in multiple states simultaneously, collapses into a single different state upon observation. Is it the act of measurement itself that forces the collapse? Or is something else at play? It's a question that continues to be debated, highlighting the inherent uncertainty and interpretive nature of quantum mechanics.
And this is where teaching quantum mechanics takes on a unique dimension. It becomes less about presenting definitive answers and more about fostering critical thinking, encouraging students to grapple with these fundamental questions and explore the various interpretations of quantum mechanics. After all, science is a constantly evolving process, and nowhere is that more evident than in the realm of quantum phenomena.
Precisely. And there have been groundbreaking experiments that continue to deepen our understanding of these quantum mysteries. Take, for instance, the work of physicist Elaine Aspect. In 1986, he conducted a landmark experiment that provided compelling evidence for wave-particle duality, demonstrating that even individual photons, the fundamental particles of light, could exhibit both wave-like and particle-like behavior. This experiment was a testament to the remarkable ingenuity of experimental physicists who design ever more sophisticated techniques to probe the counterintuitive world of quantum mechanics.
It's amazing to think that even something as fundamental as the nature of light is still being actively investigated and refined. And as our understanding of quantum mechanics evolves, so too do the pedagogical approaches used to teach it. The research you provided highlights some fascinating innovations in this area, such as the use of interactive simulations and virtual reality environments to help students visualize and engage with these abstract concepts.
Absolutely. Technology plays an increasingly vital role in making these complex ideas more accessible and engaging for learners. By providing students with interactive tools and immersive experiences, we can, hopefully, spark their curiosity and inspire them to delve deeper into this fascinating and ever-evolving field.
So, as we wrap up our deep dive into the world of physics, from the elegant swings of the pendulum to the enigmatic realm of quantum mechanics, we're left with this sense of awe and wonder. We've explored how historical discoveries have shaped our understanding of the universe, how the challenges of teaching physics reveal the depth and complexity of these concepts, and how the quest to unravel the mysteries of the quantum world continues to push the boundaries of human knowledge. And to you, our listener, we encourage you to embrace the power of curiosity, question assumptions, and never stop exploring the intricate tapestry of the universe. Who knows what incredible discoveries await us just beyond the horizon?